works at City University of New York and also Lehman College. And she's going to tell us about the quantum Hall effect, topology and dynamics in arbitrary dimensions. Thank you.
Well, first, I would like to thank the organizers for their hard work in putting such a unique conference together. And it's my pleasure to participate in my first WIMP and also meet all of you. Okay, so this talk is on quantum Hall effect. This is mainly an experimental phenomenon on systems, on materials where electrons are confined to move on a two-dimensional surface and where there is a strong magnetic field perpendicular to that surface. The effort to understand theoretically the phenomenon revealed deep connections with topology, fuzzy spaces, index theorems, which I think might be some interest in this conference. And let me give you a brief description of this phenomenon. First, let me start with the classical Hall effect, which was introduced by Edwin Hall, experimentally observed in 1878. So we have a material here. Electrons move on this two-dimensional surface, and we apply a voltage along this x-axis in order to drive a current through this x-axis. But because there is a magnetic field, as the charge carriers move, they bend because of the Lorentz force that we learned in our introductory physics course. So as a result, there is a built-up electric field here and a built-up Hall voltage, the so-called Hall voltage. So experimentalists measure the Hall resistance, which is essentially this Hall voltage divided by the current. And this is proportional to B because it's B that created this Hall voltage. And then there is the other more common resistance, the longitudinal resistance, which is the V over I, Vx over Ix. And this does not depend on B. And this is the diagram. So this is the Hall resistance as a function of B and the longitudinal resistance as a function of B. Okay, 100 years later, almost 100 years later, now we have technology of having very low temperatures. So now this is in room temperature. As we decrease the temperatures very low to almost 0 Kelvin, what we observe is the following. So this is now the diagram. This is B, and this is rho, the whole resistance. But instead of being, it's essentially linear, rising with B. However, there are these plateaus. The formation of these plateaus. And what was very surprising is that on these plateaus, the resistance, the Hall resistance, is quantized because this mu is an integer number. And the precision of the quantization is 1 to 1 billion. Okay, so remember, these are man-made materials. There are impurities, there are imperfections. No matter what, this nu is integer and does not depend on these issues. Okay, this was discovered by von Klitzing in 1980s, and he got a Nobel Prize a couple of years later. And another way to write this is in terms of the Hall conductivity, which is the relation between the longitudinal current and the perpendicular electric field. And this Hall conductivity is essentially the inverse of that. So this is one of the most precise experiments in physics. And this experiment is also used to measure the fine structure constant. Okay, another way, independent. And this is used now as a measure, as a standard for resistance. Okay, another surprising result a few years later was that there are also plateaus that appear for particular fractions for nu. So nu is 1/3, 1/5. Particular fractions, we also observe these plateaus. This it goes under the name of fractional quantum Hall effect, observed by Chu and Stormer in 82, and also got a Nobel Prize a couple of years later. Okay, so in this talk, I'm going to talk about the integer quantum Hall effect, because in that case, we can understand the physics and the dynamics in terms of free electrons. For the fractional quantum Hall effect, Coulomb interactions play a very important role, and there is not an analytic understanding why these particular fractions appear. Okay, so now the physics on these plateaus is the physics I'm going to essentially discuss today for the integer case, and it has been used as a framework for interesting ideas. As you will see, there are conformal and topological field theories involved. There are fuzzy spaces. There are so-called bulk edge dynamics and bosonization. Okay, so we'll start with free electrons. And in fact, because we have a very strong magnetic field, the spin aligns along the magnetic field, so we can neglect the spin degree of freedom. So essentially, we have two-dimensional charged particles moving in a strong magnetic field. This is the so-called Landau problem. So we solve a Schrödinger equation. This is the simple Hamiltonian. We choose the gauge field, so it gives me a magnetic field B perpendicular to the surface, and I look at the spectrum. So what we find is that the energy spectrum decomposes in discrete Landau levels. And the difference, the energy difference between two consecutive Landau levels is of order B. So there is a big gap appearing between these Landau levels. Now, each Landau level is degenerate, and the degeneracy is essentially proportional to the magnetic flux, proportional to the magnetic field, and proportional to the area of the material. And the nu that we saw before in this picture is essentially the number of completely filled Landau level, and no surprise, these are integers. Okay, now we want to look at the many-body problem. So electrons obey exclusion principle. So on each, and we are going to fill out the first Landau level. So for each state, we can only put one electron. And once we fill that, the state is kind of incompressible. We cannot force the electrons to come closer together because of the exclusion principle. And it costs too much energy to jump to the next Landau level. So this is an incompressible state. Now, by the way, let me say one more thing. I can explicitly write down the wave functions. This is simple particle wave functions on the lowest Landau level. This Hamiltonian up to a constant is given in terms of a covariant derivative, d and d bar. So the d bar on psi is 0, gives me this kind of the wave functions, which up to this exponential factor, they're holomorphic functions. Now we want to look at the many-body problem. Now, in talking about the degeneracy here, I kind of neglected the finite size of the material. And essentially, because the material is finite, at the edges, there is like a confining potential to keep the electrons inside the material. So the Landau levels get slightly deformed at the edges. So they come like this, they appear like that. So still, the bulk electrons here cost too much energy to go up here. But the electrons at the edges, we need very little energy to move them around the edge. So essentially, the dynamics is completely confined on the edges. And this is what we are called incompressible quantum Hall droplet that has boundary fluctuations. Incompressible because the density is constant here, and we can only deform a little bit the areas that has the area that has to do with the motion of these outer electrons a little bit here, this small energy effect. Okay, so these are the so-called edge excitations, low energy excitations of the system, and correspond to area preserving diffeomorphism. So we have a droplet, we have a fixed number of electrons, we cannot change that. So essentially, this kind of droplet just changes a little bit the shape. Okay. There is this edge dynamics, which can collectively be described in terms of one-dimensional chiral boson. No, it's something, it's there because the area of the droplet cannot change. We have fixed number of electrons. The area is fixed inside the droplet. So that's incompressibility. It's just only the edges move, only the boundaries move. And so we can describe the dynamics in terms of one-dimensional chiral boson. Like this has to do with the slope of the confining potential. So if we write the equations of motion, the propagation is along a particular dimension, along the boundary. And the chirality here is very important, and we can even understand it classically, because suppose this is our sample, we have a magnetic field perpendicular to that area. So the bulk electrons just go around in cyclotron motion because of the magnetic field. But when these orbits hit the boundary, they have to bounce back, and because of the magnetic field, they can only move along one direction. So this chirality has to do with the presence of the magnetic field. Okay. However, now, so in physics, we are many times interested in long wavelength description. So in that sense, we can integrate out the microscopic degrees of freedom, which in this case are the electrons, and we find an effective action. And here we are interested in introducing gauge fluctuations into the system in addition to the constant magnetic field. We want to see how the system responds and what is the effective action. Okay, well, people have done that many ways. One way is to completely integrate out. We know this action, we can integrate out the fermions. And what we find is that the action, the bulk action, is described by a Chern-Simons action in this form. And the coefficient here is related to the Hall conductivity, as it should be, because once we have this action, we can calculate the response of the system to electromagnetic fluctuations by taking the derivative with respect to A mu. This is the current. And this is essentially the relation that I showed you before. This is the JI. This one here is the electric field perpendicular to JI. And this is the conductivity. And here I set the E and H bar to 1. So this is only mu over 2 pi. Okay, now, however, let's look at this action. If I make gauge transformations, there is an overall surface term remaining. So if this manifold has boundaries, then the Chern-Simons action is not invariant under gauge transformations. However, we started with a theory that has to be gauge invariant. And in this case, we have also the edge dynamics. The edge dynamics now is described by a gauge chiral action, which also has gauge anomalies. So if we put the two together, there is an anomaly cancellation between the two. And this shows that there is a tight correspondence between the bulk and the edge action so that anomalies cancel. Okay, now another question that people ask is, how does the system respond to stress and strain? So even if I'm on a flat surface and I deform a little bit the lattice, what happens to how does the system respond? So for that, one has to calculate the stress tensor. We couple theory to gravity. This is a non-relativistic system. Okay, so this was done and by these people. And what they found is this effective action. This is also a type of Chern-Simons action, but in addition to ADA, I have now the presence of a spin connection. And this S, the index S, when S is 0 is the lowest Landau level, S equals 1 is the first Landau level, and so on. So the stress tensor can be derived by varying the effective action with respect to the metric. And we find an expression like that. And this coefficient here is called Hall viscosity. So the Hall viscosity and the Hall conductivity are two important transport coefficients in the quantum Hall effect literature. Yes.
You just mean geometry and not gravity? Do you,
Yeah, but
do you
it's-
mean gravity as, you
So-
said a non-relativistic, so I didn't quite understand.
Yes.
It feels like there's geometry here, so you've got a.
Yeah, so even in the flat background where Gij is delta Ij, I can deform it locally.
Right,
That creates some kind of local curvature
yes.
and it creates a spin connection. So
right.
that's what
So
I
it's
mean.
Just geometry.
Yes.
Not specifically gravity. Yeah.
Okay, I mixed the two. Yes, yes, I may use that again. Okay, so there are three effects that we saw in 2 dimensions. The edge action when the background field is constant, and then when the background field changes, the Chern-Simons action, and then when the metric changes or geometry changes, we find this effective action. So now what I want to see how these 2 features, 2-dimensional features, extend to higher dimensions. And this is the core of my work on this topic. So the first effort to extend quantum Hall effect on S4 was done in 2001 by Hu and Zhang. They introduced an SU2 magnetic field. And right after that, in collaboration with Paramesur and Nail, and most of this work is in collaboration with Paramessuran, we generalized this to arbitrary even dimensions by formulating quantum Hall effect on complex projective manifolds. Now, this has 2 nice features. The first is that it introduces higher dimensionality, and we can systematically, for any K, study the quantum Hall effect in these manifolds. And also it introduces the possibility of having both abelian and non-abelian magnetic fields. So in the case of non-abelian magnetic fields, we think of these electrons as having an internal degrees of freedom. Now, when we started this work, and since then we have written several papers, just extending it to higher dimensions was just an interesting mathematical exercise. However, to our surprise, a few years ago, there are experimental results now on 4-dimensional quantum Hall effect. And 4-dimensional mean 4 spatial dimensions. Okay, by introducing the so-called synthetic dimensions, which I will talk a little bit later. So these are not real dimensions the way we have, but there are dimensions in internal spaces, which I'll describe a little later. Okay, so we can make a contact with the experiments now. Okay, let me say a few things about the complex projective manifolds. These are 2K dimensional spaces. They're locally parameterized by complex coordinates. They're endowed with the so-called Fubini study metric. And from here also we can read out the Kähler-2 form by creating the wedge here. Now, a very important property of these group cosets is the fact that they are written as group cosets. I'm sorry, they are group cosets. So CPKs can be thought as SUK plus 1 mod UK. And it is property that allows us to construct the full spectrum of quantum Hall effect and all easily and systematically and all the Landau levels. Okay, so yes.
Stress energy density vector, S effective upon stress energy density, as we would write it in GR, S effective variation. Okay. Yeah. So I'm just saying that the stress energy expression looks just like we would write it in GR. But here, the G's, so is it a dynamical theory of the geometry?
No, these are fixed G's.
The geometries are just fixed? So
yeah, it's fixed for
have,
CPK.
Okay, so you're not going to be, because the deformations you were talking
I
about
will come to the deformations
So
later.
then you'll have a,
Yes,
that will come into the dynamic.
yes. So far these are fixed because you see this for the CPK curvatures, they take values in UK and they're constant.
Yeah.
And in fact, we're going to use this idea to take the magnetic fields proportionally to curvatures because we want to have constant magnetic fields on these spaces.
May I
Okay.
ask a question? I didn't quite hear what Sumati asked, so maybe it's related. So you're looking at SUK+1 as fibered over CPK?
I'm sorry?
Are you looking at SUK+1 as a fibered manifold above
Yes.
CPK?
Yes,
And
yes.
so gauge theory and that principal bundle, UK principal
Yes,
bundle.
yes.
Okay, thank you.
Yes. I hope yes. Yes. Okay, so we can explicitly find the spectrum, and I will say a few things about that. So again, we find degenerate Landau levels, which are separated by energy gap. And each Landau level forms an irreducible SUK+1 representation that has particular charges, UK charges, and it's very easy to calculate the degeneracy and energy and stuff like that. So we can write a full spectrum, single particle spectrum. Okay, just to give you a flavor of how this works, let me start with the smallest of them, which is the sphere. And quantum Hall effect on a sphere was analyzed several years ago by Haldane, but now I'm going to use this group theory approach to show you how we proceed. So here is the sphere. So we have a magnetic field perpendicular to that, which is created by a magnetic monopole at the center of the sphere. So because of the Dirac quantization, the magnetic flux is quantized. So B is essentially proportional to N. There is this relation here. And so we are going to think of this as this coset, group coset. So we can parameterize it in terms of an SU2 matrix. And in fact, we can explicitly write the dependence on the holomorphic and anti-holomorphic coordinates Z. Okay, so we think of translations in this space corresponding to right rotations, to right transformations, such that G and GH, if H is in U1, are identical points. And so we write these operators are, these are the right translation operators. And the coset right transformations, other than the U1, we put them in complex combinations. So we have the R plus and R minus, which are essentially the covariant derivatives of this manifold. And of course, the commutator of this gives me R3, but this is like the magnetic field because these are covariant derivatives. So this will be, in fact, because I put this I, this will be minus 2B, which means that the action of this R3 on psi has to give me minus N/2. So this has a very particular right charges. So the wave function, I can write as in terms of the Wigner functions like that, which is, this is just the matrix representative of G in a particular representation. However, because R3 on psi has to be minus N/2, this fixes my M prime to be minus N/2. So this right state is fixed for me. Okay, so we can write the Hamiltonian. The Hamiltonian is written in terms of essentially the covariant derivatives, the holomorphic and anti-holomorphic. And because of that, the lowest Landau level is characterized by R minus on this state, R minus on this state being 0. So this now is the lowest weight state in the representation. If we know the lowest weight state, we know the full representation. So the lowest weight state is the N+1 representation, SU2 representation. Now, we can similarly think about higher Landau levels. This state, the J minus N/2 for a higher Landau level is not the lowest. The lowest one is created by going S steps down. So this is the lowest weight state, which immediately tells me that the dimension of this representation is N plus 2S plus 1. 2 of this plus 1. Okay, so I can work like that for each Landau level. I know the wave functions, I know the degeneracy, and so on. Okay, so the spectrum decomposes into these Landau levels, and each Landau level forms an SUT representation. And the lowest Landau wave functions are of this form. Now, because we are on CP1, the exponential that we had on the two-dimensional surface changed into this. This is the metric dependent thing. Okay, so very similarly, we can work out the spectrum on CPK. So let me say a few things. It's a little more complicated here because we can have non-abelian gauge fields. Again, the translations correspond to right rotations, where G and GH, if H belongs to UK, are identical. So the UK right transformations, we can think as gauge transformations of the system. And the rest of them, we combine in complex combinations, and they give the covariant derivatives. The commutation of the two covariant derivatives takes values in UK. And how the wave functions transform depends on the choice of the background fields. Okay, so now we have a choice. We can either have a U1 background field, as we had before for this S2, but we can also add non-abelian gauge fields. And the way we choose the non-abelian gauge fields, field strengths, is we have them to be proportional to the components of the curvature. And the components of the curvature for CPK are essentially the SUK structure constants in a tangent frame basis. Okay, so essentially, again, the wave functions are these Wigner-D functions, but now the charges of these right states are fixed. So the U1 charge is proportional to N. These factors of K have to do with the normalization of SUK plus 1 matrices. And however, because we can have non-abelian gauge fields, in that case, the wave function has an internal index and can belong to some SUK representation. Okay, so such as to put it together, the wave functions are of this form. This has a particular U1 charge, which is proportional to N, and this is crucial because we're going to take N to be very large eventually. But it can also be some finite SUKR representation. We called it J tilde. And the internal index that goes from 1 to N prime, these are internal indices, and this M here is Ramsey degeneracy within a Landau level. And again, the lowest Landau level is given by this expression, which we think of as the holomorphicity condition. Okay, it fixes this as a lowest white state, so we know the full representation. Okay, so just to give you an example, if I have only a U1 magnetic field, the wave functions we find are essentially the coherent states for CPK. Okay, so now what I want to do is put aside this information about the single particle spectrum and think in more general terms about the dynamics of these droplets. Okay, so suppose we have a quantum Hall effect on a compact space M. Then the lowest Landau level defines a finite n-dimensional Hilbert space. And so we think that out of this, K states are filled, and then the rest are unoccupied. So this gives me an idea of the occupancy metrics. And if there is a confining potential, I start filling from the lower energy states to the higher energy. Okay, now what are the most general transformations within that preserve the lowest Landau level condition? Are unitary transformations that act on these metrics. So they reshuffle the electrons in different states, but within the lowest Landau level. Okay, so under time evolution, ρ0 changes to some ρ, which is U ρ0 U dagger, and this U is an n by n unitary matrix. And in a sense, this matrix U acts as a collective variable which describes the excitations within the lowest Landau level. Now we can write an action for this U, or the action is of this form. V is the confining potential. And this leads to the evolution equation that we expect. Now, it's important here that this is a universal matrix action. Okay, these are matrices, n by n matrices, has no information at all about where, what space we define quantum Hall effect, whether we have a billion or non-abelian nature of fermions and stuff like that. This is a completely matrix action. And how do we introduce the features of the space, of CPK space? In the following way, the way we do it in non-commutative field theories. Okay, so this matrix action, we can rewrite this way where we do the following. For each matrix, I define the corresponding symbol. So symbol is essentially a function on CPK in this case. So how do we define symbols?
So of course, so you're talking about our own non-abelian, but yeah.
Okay, this
So
is independent of the particular structure that I have. This is a general thing.
Yeah, so but where does a I guess when you think of non-commutativity, you think of it in terms of phase space or something like this.
There are many ways non-commutative entries. Non-commutative entries right here, because these are matrices. This is a finite n Hilbert space. So everything is in terms of n by n matrices, non-commutative.
And so, okay, so it's non-commutative in the non-abelian sense of the group that you have, or?
No, not in that sense. In the metric sense, it's non-commutative. Also, a projection to the lowest Landau level introduces, there is an inherent non-commutativity. For example, suppose you construct the position operators, x and y operator within the lowest Landau level, they do not commute. So it is a like a phase space, essentially, okay? Okay, so I write this like that. This is, I call a non-commutative field theory in the following sense. So I replace the matrices by the corresponding symbols. Symbols are just functions, they're fields, essentially. So this is a field, this is a function, this is the confinement potential. And how do I do that? For each operator, for its matrix A, I sandwich it with the single particle wave functions, and this will define a function for me. That's what I call a symbol. Then what this here is the so-called star product. How do we define the star product? Well, if we take the symbol of a matrix of two, of a product of two matrices, this is what we call symbol. And this is an infinite expansion in derivatives. The first term is just AB, the product of two functions. But then the next term is 1 over n. This is essentially the anti-holomorphic derivative on A. This is the holomorphic derivative on B, and so on. So this is an infinite series of higher derivatives. Okay? So that's the star product. And the star product is not commutative. So this essentially is a kind, if I expand, it's a non-local field theory. There are many, many derivatives, stuff like that. And then the trace from here is replaced by n, which is the degeneracy, the dimension of the Hilbert space, times the volume element, integrated volume element of the space I work on. So I go from a completely universal matrix action to something that lives on CPK, but is non-commutative field theory. Okay, so I claim that this action here describes the dynamics of the lowest Landau level. Okay, now this has been used in a two-dimensional plane context before, but now we can generalize to any dimension. So now what I'm going to do is I'm going to take the large n limit. So essentially, I'm going to ignore these terms, and I'll use here for a star product these first two terms. So the surprising result is that once I take that large n limit, this action becomes a chiral boundary action. Okay, so let me show you that. Okay, so now let's say that we have only an abelian background magnetic field. So we can write this matrix U in terms of e to the I phi, and we can define the symbol for this phi. This is the boson field that, let me come to the result. So what we find is that the original action becomes an action, a chiral action that lives on this boundary, on the droplet boundary. Now, if this was a if I had started with a two-dimensional space, this will be the boundary of the droplet of my disk, essentially, and this will be the tangential derivative to the circle, to the disk. Now, this is a higher dimensional droplet. For example, for CP2, this will be an S3, but I have many tangential directions for S3. However, the system chooses a particular one. This is essentially the Poisson conjugate to the radial derivative. So the system, although it's a higher dimensional system, can be thought of as a collection of one-dimensional chiral fields because the propagation is along one dimension. It's related because of the star product, yes. N, so the parameter is B, the magnetic field B, which is proportional to N. So, okay, let me go back. See this one here? This is the parameter, N. And N is essentially the U1 magnetic field. N is discrete here, yes, because it's the charge of the monopole. 1 over N. Yes, like an H, yes. Yes. Okay, so, okay, let me go back. Okay, so this is an important thing, which essentially is also observed in these four-dimensional quantum Hall effects. Although the droplet is a three-dimensional and you can have arbitrary directions for these fields, there is one particular direction that is chosen. And although it's higher dimensional, it can be thought as a collection of one-dimensional chiral fields. Now, one important thing it's a key ingredient that we use to derive this, is the fact that I said the star product is non-commutative. Okay, so essentially in the large N limit, the star product, the star product commutator is essentially the Poisson bracket, where this now acts as a symplectic form. Okay, so this is a nice feature. Okay, so this was derived when we had only an abelian magnetic field, but we can repeat when we have non-abelian magnetic fields. So the wave function in this case is, as I said, is a non-trivial representation of SUK. So there is an internal index. So the symbol is not just a function now. It is an n prime by n prime matrix valued function. So the action that we find, we can write it in terms of this G, which is a UN prime. And what we find as the effective action is essentially a generalization of Vesumin-Witten action in higher dimensions. And again, this derivative here, this one is the covariant derivative along a particular direction. These are the A hats here are the constant background fields, the non-abelian magnetic fields. And as you see, this is like the two-dimensional Vesumino term, but here we have to augment it with enough omegas in order to match the dimensionality of the space. Okay. And again, the theory, although it's higher dimensional, can be thought of as a collection of non-abelian chiral fields propagating in a particular direction. Okay, so these two actions that I showed you are the actions when the magnetic fields are constant. Now we want to repeat what we saw in the 2 dimensions, and we want to introduce gauge fluctuations. So how do we do gauge fluctuations? In the matrix version. So we do the following. So in the presence of gauge fluctuations, what we do is we replace the time derivative with a covariant time derivative of this form. So the matrix action, this is what we had before. So now we have this extra term. And again, we can go from here to a non-commutative field theory on CPK by replacing the matrices with the functions, with the fields, and the products of matrices with star products. Okay, but the question is, how is this script A related to the gauge fields, which are coupled to the original fermions? Well, okay, so if we look at this action here, this action has an invariance. This action is invariant under this transformation. And however, this action has to describe the initial gauge interaction. So somewhere there should be the usual gauge transformation. So the usual gauge transformation in terms of the gauge fields is this. And the strategy to use, we write script A as a function of the gauge fields, so the fluctuations, the background fields, and maybe the confining potential, and this lambda in terms of the gauge parameter lambda, so that if we do gauge transformations here, that induces the transformation on script A, like this. Okay, so we build essentially the required gauge transformation. So we find these functions. So we take the script A in terms of these gauge fields. We put it back into the action here. Put it back into the action. We take the large N limit. And what we find is that the action now decomposes into 2 parts. It's the edge, the boundary part, which was the Vesumino Witten, but now gauged, chirally gauged with this is the fluctuation of the background field. And then there is a bulk action, which is essentially the 2K plus 1 dimensional Chersanos action. Again, the same features that we saw before in 2 dimensions. Each one of them is not gauge invariant. But if we put them together, normally the gauge anomaly is canceled. And again, we see how there is a tight relation between the bulk and what we have to have as an edge action, so the anomalies get canceled. Okay. This construction of the effective action used the star product. And for the star product, we had to know the wave functions for CPK. So this construction does not allow us to deform CPK, okay, because we need the wave functions and for CPK and the star product. Okay, so we have to find another way now to deform a little bit the geometry of CPK. Okay, so how do we do that? So now we want to introduce metric fluctuations or geometry of whatever. Okay, so we're going to use an idea from index theorems. So the lowest Landau level obeys this holomorphicity condition. And we know that for complex manifolds, the number of normalizable solutions is given by the so-called Dolbeau index. Okay, so what is the Dolbeau index? This is a number, this is an integer. The integrand is given by the so-called Todd class and the Chern character. The Todd class is essentially traces of powers of the curvature, and the Chern character involves traces of powers of the field strength. But the idea is that because this is topologically invariant, we can introduce fluctuations in these curvatures and fluctuations in the field strengths, and still this remains the same. But the index, because it's the number of the normalizable solutions, is also the degeneracy in the lowest Landau level. Okay, so we are going to consider a fully filled lowest Landau level. there the degeneracy is going to be this index. But if we think that each state is filled by a particle that carries a charge E equals 1, let's say, this is also the charge. Oh, ooh, okay, this is also the charge. So that means that the Dolbeault index density, the integrand here that we can perturb around these constant backgrounds, can be thought of as the charge density, J0. But the charge density is related to the effective action, because if we vary the effective action with respect to A0, we find the charge density, which is the Dolbeault index density. So we know this side, and now we want to integrate and covariantize to find the effective action. So we have done that, and we can find, so here is what we find for the effective action, which is what people found before, but also we can do it in higher dimensions. This is the case of CP2, which is SU3 mod U2 for an abelian gauge field, and we find this effective action. Omega 0 is the U1 part of the spin connection. There is also an SU2 non-abelian part here. But we can do that for arbitrary dimensions, higher Landau levels, non-abelian magnetic fields. It's a general procedure. Okay, starting from an index theorem, we can construct all these effective actions. And having the effective actions, we can calculate the responses, the electromagnetic responses that are given by this current. Okay, for example, here I have 2, 4, 1. This is important because this coefficient here in front of this is essentially the whole conductivity in 4 dimensions that has been measured in the 4-dimensional quantum Hall systems, and we can make a contact with the experiment. Okay. Yes. Similarly, we can find the corresponding viscosity tensor, but I'm not going to talk about that. There are more response function in higher dimensions. Yeah, I had a part to talk about entropy calculation in the systems, but I will skip the entropy calculations and we'll come to the end. This, I think, yeah. Okay, so just a summary that quantum Hall effect on these spaces is a platform to study the effect in arbitrary even dimensions. And here is what I talk about experimental realizations. So this synthetic dimension is the following. There is, for example, one way to introduce synthetic dimensions is in a lattice of cold atoms, but each cold atom has internal states, can be spin states, can be momentum states and stuff like that. So by shining a laser, one can make the electron go up these different states. So essentially, this is a new dimension that they create. So there are 3 real dimensions where electrons can move on a lattice. And there is this internal dimension, the 4th dimension. So they can actually do a lot of things. We can have lattice sizes of 10 sides and stuff like that. It's very cool. Anyway, so the 2 main effects that they see is this propagation along the particular 1 dimension for the droplet in higher dimensions, as I said before, and the whole conductivity that agrees with what I showed you. Okay, so this is, we have a universal matrix action, corresponds to a non-commutative field theory. We used the index theorems to calculate the effective actions. I did not talk about the entanglement entropy. And then a question, of course, is how to extend these ideas to fractional quantum Hall effect. And we did some recent work on constructing effective actions for some of the fractional quantum Hall effect states. Okay, thank you.
The fractional case, do you use the same method or there are sensible differences?
No, for the fractional is complicated I can tell you more details later, but essentially you think of an electron as made out of m partons, where m is an odd number. Okay, and each parton lives in a nu equals 1 state. So, and they're coupled with some gauge fields. So you write the effective action for that, but then you see there is an anomaly and you need to cancel the anomaly. So we introduce fields to cancel that. So it's a little complicated process. So it's a parton construction, which is artificial because partons are not real things, but you do it just to write the effective actions. I'm sorry? We get similar results for the 4-dimensional case that we looked, but the coefficients in front of the various terms. So if I go back quickly. Okay. Okay, so essentially there are different coefficients here. So this is an ADA term. If there is a fractional effect, there is 1 over m in front of this term. Then there is omega 0 dA term. There is a factor that depends on m. So the same kind of things, factors here, ADA, omega d omega, mixed terms, but with coefficients that depend on m. That's what we find.
Thank you for your presentation. So I didn't quite understand the jump from the abelian to the non-abelian case. You replaced the curvature by something, by art twiddle. Is that right? You said.
Okay, so the thing that
Geometric,
for the non-abelian
do?
case, okay, so.
No, at the end, what I was interested in was in the Dolbeau index, how you modified the curvature in the Dolbeau index.
So the field strengths for the non-abelian case, the constant field strength is taken proportional to R. But then how we modify that? Okay, so these are, okay.
What I'm interested in is what did you do geometrically? The curvature is a geometric object. So what did you do geometrically?
So here, for example, R can be perturbed by some term, and we can independently perturb F away from the constant term. So,
but what in perturbing R, you perturb the geometry. Can you give a geometric interpretation to this perturbation?
But this is away from the constant background now.
This is?
Away from the constant background. We are going away from the CPK.
Yeah, okay, so it's a non-commutative object. What is it? There must be some maybe non-commutative geometric object behind it. Okay, okay, that's all.
Yes, there is.
That's all. Okay, okay, so it's just the structure group. The structure group has changed.
Yeah, so
okay.
This is just the construction for the effective action, and it's a large N construction. Once you have that, there is nothing non-commutative there. Non-commutative in the terms of star products and stuff.
Sorry, I think maybe it was very quick, but how is this topological information related to the deformation, the star deformation?
So what
I'm really missing this point.
Yes. Okay. So if I can use CPK here. Okay. So I'm going to find the index, the degeneracy that I have found before. However, I can slightly perturb this R away from the constant background of CPK, so that This index is fixed, does not change. Because the index is topologically invariant, so by doing small perturbation in the integrand won't change that index. That's what I do.
Yeah, you see, there is some change in our, I think you're modifying the geometry, but I don't, we can discuss that later. Yeah, we can discuss that later. Thank you.
Okay.
So you were dealing with a continuum and you were generalizing it to higher dimensions. What if I have a lattice, discrete lattice, and will the geometry of my lattice be of any importance? Or is it because you're taking a hydrodynamic limit, like you're considering large scales, that won't be relevant?
Well, in fact, in the case I discussed experimentally, they look at four-dimensional quantum Hall effect. The space is essentially two complex planes. And the good thing about CP2, let's say, is if you take R going to infinity limit, essentially decomposes into complex planes. So the lattice is on these planes.
No, I'm saying that suppose I have a square lattice and my electrons are confined to that, like it's not a continuum anymore.
Say that again, I'm sorry.
If I have, say, a square lattice versus a triangular lattice, so it's not, suppose 2-dimension only, but not continuum, but just discrete, will that make a difference?
I don't think so. Because anyway, in practice, I talked here about in terms of free electrons, but in materials, of course, electrons are not free. They live in electronic bands in a Brillouin zone.
Yeah.
Okay, so no, I don't think it will make a difference.
So that is basically because you're taking the like you're looking from a large scale. The details of the lattice, they are not important because you're looking, you're coarse graining.
No, here I don't look at the lattice. I look at the continuum.
Okay. But what I'm saying is that because you're looking at an effective theory of some large scale dynamics, is that because the details of the lattice are not important?
Effective theory in the sense that I have integrated out electrons.
Yeah.
Yeah.